Say you're a farmer and you only have 1,500 feet of fencing. What's the largest rectangular area that you can encompass with this amount of fencing so that your sheep have a large grassy area to eat, play, and baa as they please? First, we need to find a function that represents the fenced area with respect to the side length x. Knowing that the area of a rectangle is its width times its length, the width of the rectangle can be represented as 750 feet minus the length of the rectangle x. By substituting in 750 minus x for w, we can then find out that with 1,500 feet of fencing, the function is f of x equals 750x minus x squared. Now, if you have a graphing calculator, it's pretty easy to just throw the function in, let it graph it, and estimate about what side length creates the largest area. But if you want to find the exact side length, we can use the function's derivative. Try looking at the graph and thinking about what happens to its derivative at and around the maximum point. Hopefully, you notice that the derivative at the maximum is equal to 0. Any x value where the derivative of the function is equal to 0 is known as a critical point. Extremum, or maximums and minimums, occur at these critical points. But you can't just figure out where a derivative is equal to 0 and assume that that's an extrema. Critical points at which the second derivative is also equal to 0 are known as an inflection point, and at these points an extrema cannot occur. An example of this is at x equals 0 on the graph f of x equals x cubed.
So how do we figure out what critical point is a minimum or a maximum? If you look at the graph, you'll hopefully notice that the derivative changes from positive and negative as x increases. This is what indicates to us that it's a relative maximum. Relative minimums are the opposite, where the derivative changes from negative to positive, and inflection points show no change in sign at the critical point. With this information, we can find out if a critical point is a minimum, maximum, or neither without looking at a graph. So now using this method with our function, f of x equals 750x minus x squared, we can find its derivative, f prime of x equals 750 minus 2x. Then find that the derivative is equal to 0 at x equals 375. Now if the equation is only defined on a closed interval, you must make sure that this point is our absolute maximum value by comparing it to the function's value at the endpoint to ensure that our critical point is the absolute maximum and not just a relative maximum. An absolute extrema is the point on an equation where the function reaches its highest or lowest point, and a relative extrema is where the equation reaches a point that is relatively higher or lower than its surrounding points. Our function is only defined on 0 to 750, since we cannot have negative area. Now, with this table of values, it can be seen that the absolute maximum indeed occurs when the side length x is equal to 375. This method can be used for the optimization of any differentiable function. Let's say that our friend here, Bob, is shot with an arrow and starts bleeding, but luckily, Bob's friend Bill is a paramedic and immediately starts pumping blood back into him for 4 minutes. The amount of blood in Bob's body in liters is represented by this function, where t is time in minutes. What is the lowest amount of blood that Bob has on the time interval 0 to 4 minutes?
For this problem, the function is a given, so it does not need to be identified. Next, take the derivative of the function, and then find where its derivative is equal to 0 in order to identify critical points. Find the derivative on either side of these critical points to determine if they are maximums, minimums, or inflection points. From here, plug the critical points you are interested in into the original function and compare these points to the values at the endpoints to find the absolute extrema. Using these steps, it can be determined that Bob had the lowest volume of blood at t equals 3.5 minutes, where he only had 1.96 liters.